All right, let's talk about a technology that promises to change everything. I mean, we're talking about the power to cure diseases, to design incredible new materials. But what if that very same power could also be used as a master key? A key to every secret we've ever stored digitally? Well, that's not a movie plot. That's the reality, the paradox of quantum computing. And that's the central question we're facing right now. How can something with so much potential for good also pose one of the biggest threats to our global security? It really is a crossroads. So how did we get here? And more importantly, where do we go from here? Okay, so to really get a handle on the risk, we first have to understand the machine itself. You see, there's this global race happening to build a truly powerful quantum computer, but it keeps hitting the same fundamental wall. It's a problem of scale. At the very heart of these machines are something called qubits. Now, the thing about qubits is they are powerful, but they're also incredibly sensitive. They're fragile. As you try to pack more and more of them together on a single chip to get more power, they get really unstable. The slightest little thing, a tiny change in temperature, a stray magnetic field, what scientists call noise, can throw the whole thing off, causing all sorts of errors. And that has been the single biggest hurdle in this whole race for quantum power. So what's the workaround? Well, instead of trying to build one single massive perfect quantum computer, the field is pivoting to a distributed model. You know how today's supercomputers aren't just one giant processor, right? They're actually thousands of smaller computers all networked together. Well, distributed quantum computing, or DQC, is applying that exact same logic, linking up smaller, more stable quantum processors to create one incredibly powerful system. So how does a network like this actually work? Well, it all starts with the quantum nodes. Those are the individual little processors. They get connected by what are called quantum links, which use this mind-bending property of physics called entanglement. Seriously, think of it like this. You have two coins that are linked. If one lands on heads, you instantly know the other one is tails, no matter how far apart they are. It's pretty wild. And that's how they share information. Then, to send that signal over really long distances, you need quantum repeaters. These are the basic building blocks of the very machine that poses this incredible threat. Okay, so you might be thinking, why should I care about a machine that isn't even fully built yet? And that is a fair question. The reason you need to care is that the attack this machine enables, it's already started. This, right here, is the crucial point. Right now, adversaries, we're talking nation-states, are actively stealing and stockpiling huge amounts of encrypted data. They can't read it yet, but they're betting that in, say, 10 or 15 years, they'll have a quantum computer that can. This strategy has a name: harvest now, decrypt later. And it means that your most sensitive data, your company's intellectual property, government secrets, even your private records, could already be sitting on an adversary's server, just waiting for the right key to be built. And that key they're waiting for? It's called Shor's algorithm. It's basically a recipe for a quantum computer designed way back in 1994 that is specifically tailored to break the types of encryption that protect almost everything we do online. A mathematical problem that would take our best supercomputers literally thousands of years to crack could be solved by a quantum computer running Shor's algorithm in just a matter of hours. So, how do you figure out if you're already in trouble? Well, there's a pretty simple formula for it, sometimes called Mosca's theorem. Just take X, which is how long your data needs to stay secret, and add Y, how long it's going to take you to upgrade all your security systems. Now, if that total is greater than Z, the time until a powerful quantum computer arrives, then your data is already at risk. For example, let's say your data needs to be secret for 20 years, and it'll take your company 10 years to migrate to new systems. That's a 30-year risk timeline. If a quantum computer that can break today's crypto shows up anytime in the next 30 years, and a lot of experts think it will, then that data is already vulnerable. Faced with that pretty sobering reality, there's a massive global effort underway to build a totally new kind of digital shield, one that can actually withstand a quantum attack. And that shield is called Post-Quantum Cryptography, or PQC. These are basically brand new encryption algorithms that are designed from the ground up to be safe from both classical and quantum computers. For years now, the U.S. National Institute of Standards and Technology, NIST, has been running this huge global competition to find and standardize the very best PQC algorithms out there. And here they are, the first round of winners. Now, don't worry about the names here. What's really interesting is the mathematical basis column. You'll see that most are lattice-based, which is a type of math that's kind of like trying to find the closest point in a huge, really complex multidimensional grid. But you'll also see that NIST chose others, like hash-based and code-based algorithms. So why not just pick one kind of math and go with it? Well, this is why. An algorithm called Psych was a super promising candidate, a real frontrunner in the NIST competition. Then in 2022, a couple of researchers broke it. And get this, they didn't need a quantum computer. They did it with a single, regular, off-the-shelf PC. It was a huge wake-up call and a perfect example of why we can't put all our cryptographic eggs in one mathematical basket. A single clever breakthrough could wipe out an entire family of algorithms, so having this diversity is our absolute best defense. Okay, so the new standards are here. The threat is real. The clock is definitely ticking. So what are organizations supposed to actually do to get ready for this massive, inevitable shift? First thing is to understand the stakes. This isn't just a tech problem. It's a full-blown geopolitical race, and the timeline is getting pushed forward by huge national investments. Just look at these numbers. China has reportedly committed around $15 billion to quantum technology. That is more than double the US and way more than the EU combined. This intense competition for a quantum advantage is what's lighting a fire under everyone else to get prepared. And you can see that urgency reflected right here in these deadlines that are all starting to line up. Governments and big tech companies are not messing around. Canada wants initial migration plans by 2026. Microsoft is aiming to be fully transitioned by 2033. And the US and UK governments have set a hard deadline of 2035 for their own systems. The message is crystal clear. This is happening, and it's happening this decade. So what does a practical roadmap for this even look like? Well, most experts say it boils down to 5 key pillars. You start with governance. That means getting buy-in from the very top. Next is inventory. You got to find all the crypto you're currently using because you can't protect what you don't know you have. Third, you prioritize. Go after that long-lived data first, the stuff that's most at risk. Fourth is building for crypto agility, designing your system so you can easily swap out algorithms if one gets broken. And finally, you do a phased transition, using a hybrid of old and new crypto to avoid a big, risky switchover all at once. And just to give you a sense of the scale here, let's compare it to the last big crypto migration we had, from DES to AES back in the day. Now, that was a big project, but it was basically a contained change. The PQC transition, this is a whole different beast. It impacts the entire public key infrastructure, everything from web browsing to digital signatures. And it requires a fundamental shift to brand new kinds of math. This is so much more than a tech upgrade. It is a profound strategic challenge, maybe one of the biggest modern organizations will ever face. So let's just boil this all down. What are the key things you need to remember? First, the quantum threat is not some far-off sci-fi problem. The harvest is happening as we speak. Second, the solution is already here. Is strategic, carefully planned migration to these new PQC standards. Third, this has to be treated as a major enterprise-level risk, not just some IT project you hand off to the tech team. And finally, and most importantly, the time to start creating your migration plan isn't next year, it's today. And all of this leaves us with one final thought. It's easy to look at this massive, complex, and expensive transition as just a giant headache. But what if it's also an opportunity? A once-in-a-generation chance to clean up decades of technical debt, to finally get our cryptographic house in order, and to build a digital world that's not only quantum resistant, but is fundamentally more agile and resilient for whatever comes next.